9-bit, why, Mr. Jenkins?
Because you need the carry.
Because I want to put the temporary carry somewhere, okay? And this is an efficient multiplier, so I'm going to use as few registers as possible. 1, 2, 3, 4. Well, let me clearly mark these 4 and then these 4. We are going to put the multiplier in here. The accumulator is big enough to hold both the multiplier and the multiplicand. Right? That's why we have 8 bits, because each one is 4. Therefore, I could fit them both in the same register. I don't need additional hardware. So I'm going to put the multiplier in here. The multiplier was originally, okay, so that's original. This is an accumulator that we said, when we shift, that's the long thing I'm shifting, right? If you go back to your previous page, or rotating, right? So it's a shift right accumulator, and it's cyclic. Well, no, actually it's not going to be. I won't need it. Okay. That's the multiplier. So I'm always going to look at that last bit coming out. Always. I don't have to determine whether I need to add or copy or not. I'm always going to look at this position. Because the next time, instead of me going to the left, I'm just going to shift the whole thing to the right. So this bit is going to be in the place I'm looking. The next time, this is going to be in the place I'm looking. So all I have to look at is that least significant bit. David?
It's a register.
That's a register, it's an accumulator. I'll go right over here. 9-bit accumulator. But an accumulator is just a bunch of fill and flux. It's a register. It's a shift register. Okay. So other than shift, so, hold on. So I need something that shifts. What else do I need? What's the other operation? Add. So of course I need an adder. Here's going to be my adder. We know how to design an adder. We did that several times. The adder is going to take the 2 numbers it has to add. Here's the other one, which is always going to be just 4 bits. And this one has the multiplicand, 1101. This is the multiplicand. That's, if I have to add, that's always the number I have to add. That one doesn't change. So this goes to the adder.
That little dash coming out from the right is just because
And that's an output that's,
only reading the least.
because that's the only one I really need
Okay.
to go to my control. Okay. I'm going to take a number. I'm going to add it. I'm going to put it back. So the adder needs to know whether to add or not. So here's the, let me call it the add signal. Big A, or add. So if A is 1, it means you have to add. Otherwise you don't add. Who produces the signal? The control system. So here's my control system. What other system did the control have to generate?
The shift.
The shift signal. So it has to either tell me add, it also generates S for shift. And if that is 1, it produces the shift pulse. this, the least significant bit, whether before or after the shift, is the one that goes into the control, right? Because it will determine whether I generate the add or I generate the shift. So that's an input. Let me call it M, or multiplier bit, or least significant multiplier bit. What else does my control need?
When
The start cell. Let me call N the start because I use that for shift. All right. So, I need somebody taller. So let's follow the sequence here. And I'm gonna have to write a little smaller. 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8, 9. This diagram will always represent my accumulator. These are the signals. Let me write them in the same order. Okay. M, which is the multiplier bit. S, which is the shift. A, which is add. Somebody I think already said it. Said, what else does the control usually tell you? When to stop. Good. So, let me call it D for done because S is already taken twice. All right, so we start. At the beginning, I don't have a carry. These are the 4 zeros, which are leading of my 8 bits because I only have 4 bits. Here's my original number, 1, 0, 1, 1. So to decide the control, what? And I need N, so N. Okay, if N is 0, what happens?
No.
Nothing. So until N becomes 1, this is the same thing over and over and over again. I don't have enough board, so the first one I'm going to do is, let's say we start. But yes, I agree, we need to start second. So if N is equal to 1, what is M?
1.
1. Again, it's always this bit. So 1. Do I have to shift?
No.
Do I have to shift now?
No.
No. Why? Because this is 1. This tells me don't shift. Because what I have to do is,
Add.
okay, copy, but I don't really have to copy because it's there already. All I have to do is add, right? Copy really means keep this number in there. So now I have to add. Am I done?
No.
All right. This said add, so I have to add. Notice the position. It's always the 4 most significant bits of my accumulator. So I add, what's the number to add? 1, 1, 0, 1. It told me to add, so I'm adding. The result goes where? Back in the accumulator. I add. What is my multiplier bit? 1. Do I shift?
Yes.
Do I add?
Yes.
Huh?
Yes.
No.
No.
You can't shift and add simultaneously. So either you shift or you add. Which one do I have to do? Shift. So no, don't add. Are you done? No, you're not done. Right? We shift followed by an add. You can't be shifting and adding because then you don't know what you're adding. You shift, not add. So I shift because I follow instructions over here, my students. And what's the result after my shift? No, I shifted.
1, 0, 1, 1.
1, go ahead.
0,
Right.
1, 1, 0, 1, 1, 0, 1.
No. Okay, this one appeared here, and then I just shift. 0, 1, 1, 0, 1, 1, 0, 1. Yes?
If we're not doing a cycling, how we going back?
Yes.
We are doing
It is,
cycling? You said
no, we're not doing cycling, sorry. I said no, so not cycling.
Oh, why are we not doing cycling?
Wait, because this design does not need a cycling shift. Because I put these in the lowest significant bit. It's much more hardware efficient than the previous one. So let's see, where am I? 0, 0, 1, 1, 0, 1, 1, 0, 1. All right, so now what's my multiplier bit? 1. Do I shift?
No.
No. Do I add?
Yeah.
Am I done?
No.
So what do I add and where?
You had 1101?
You add 1, 1, 0, 1, yes.
110.
To the second.
Yeah, the second.
Always
Right
the
there,
same. Remember, this is not moving. This is always in the same position. It takes these 4 and adds these 4. Always in the same position. So whenever I add, it's always going to be this number added. If this is a 1, always in the same position. So 1, 1, 0, 1. Uno, dos, tres, cuatro, cinco, seis, siete, ocho. Okay, 9. It's telling me to add, so I add 1, 0, 1, 1. 0 plus 1, 1, 1 plus 0, 1 plus 1, 0, carry a 1, 1 plus 1, 0, carry a 1. That's why I need that extra spot, because I could get a carry from the last bit. So now that's the content of the accumulator. You look always at the same position. What's the multiplier bit? 1. Therefore, do I shift?
Yeah. Yeah.
Yeah.
We just added, when there's an add, there's always a shift following. Do I add? No, and I'm not none. Right, so, not cyclic. So, 1, 2, 3, 4, 5, 6, 7. I shift to the right. What goes to the carry position? After a shift. Okay, so the accumulator, when I shift, the input is always 0, right? And then I have what? 1, 0, 0, 1, 1, 1, 1, 0. That's the result right now. Am I done?
No.
Okay, what's the multiplier bit?
0.
0. Do I shift?
No.
I like his
Oh,
answer.
yeah, because you have 0.
You have 0. When you have 0, will you ever have to add it? No. So this time, you just shift. Because this is 0. Do I add? Not yet. Am I done? Not yet. So I do the same shift, and I'm running out of board. What's the first bit? 0, and then 0, 1, 0, 0, 1, 1, 1, 1, 2, 3. Now we keep doing this, right? So I look at the least, I always look at this position. It says M is 1. So, do I shift? No. Do I add? Yes. Am I done? No. Okay. You will never be done just after an add. You have a break before we shift. You have a question?
Yeah, so how do you know when you're done? How do you tell it to stop?
The stop signal will be generated once you have confirmation. So that's part of your control. So, the control will also basically say, stop shifting, stop doing anything, or say stop signal.
We'll design that separately. Why is M one? M is always whatever's here, one, zero, one. It's always a bit. This is M. It's always bit. Whatever is in there, that's M. The multiplier bit. That tells you whether you have to add or not. Because this one has a zero. If you have a zero, you don't add, you just shift. Is that clear to everybody? If it's a zero, you don't add zero. When you add, the only possibility to add is this number. So if the multiplier bit is a zero, do you add? No, you just shift it in, and therefore we have two shifts in a row. And whenever there's a zero, you just shift. Multiplier bit, one, meaning? All right, what does, this is one, which means add. So I add, where? In the same position. 1, 1, 0, 1. I put it back in the accumulator, that's why there's double arrows. If I carry in 1, 2, 3, 4, 5, 6, 7, 8. 1, 1, 1, 1, 1, 1, 0, 1, 0, carry 1, 1, 0, carry 1. Multiplier bit is 1. Do I shift? Do I add? Am I done? No. Not yet, but we'll soon be because I don't have any more work. All right.
There's been an example we've done before, we did it this way, after 3 successful shifts, we knew to just cycle through. Is there any way to, like?
Yes, you are going to count the number of shifts. That's the way to do
Yeah,
it.
we're trying to have 8.
8,
From the,
whatever the size of your accumulator is.
but the examples before this, we were able to tell, that we were done with the operation, and then we shifted 5 just together without going step by step. Is there any way to tell using this method, or you just
Yeah.
have to?
We will design the stop sign. Basically, what we do is count shifts.
All right. But
And
for-
once you count it, 8 shifts.
For the table,
You're done.
though, we have to go step by step.
Oh,
For
yeah.
this,
Yes. All right, so, am I done? What do I have to do? Huh? Gotta shift, how many times? Okay, it's actually 5 more times, or until the control tells me stop shifting. We still have to define that. So,
Get 5, 3, and 9 dealers.
now, the result is just, remember, I don't care, it's gonna be here. It's always gonna be in the least state significant bits. That's a temporary carry.
So this
It's
is,
not part of your result. What?
this isn't cycle, right? This is not cycle.
No, cycle.
So when we shift,
When you shift, the input from the right is always a 0. I had drawn it and just erased it.
always 0?
Yes.
Why?
The new bit coming in, this is a shift register.
That's from, the one is from the.
This,
Oh, okay.
it's a serial input which will always be 0.
Uh,
Okay, because it's not
so it's
circular.
not-
Alright, so we shift, and eventually, what is going to be MSAD? When I'm really done, well, let's put the contents. That's my carry, 1, 2, 3, 4, 5, 6. So here's those 4, and those 4. When I'm done, what are my contents? On tens. What's gonna be in here?
1.
No.
0.
When you're done,
Oh, 9 bit, sorry.
0, 1, 0, 0, 0, 1, 1, 1. Alright. That's that's really how a multiplier operates. It's less intuitive, but it works well and it works the same each time. So there's a simple control that needs to be designed.
In this situation, I think we have to just shift one time. So we
Hey.
have to do that.
So we had shift, and you shifted, and you get that answer.
Yeah.
Remember, because the multiplier started in these 4, so shifted 4. Okay, so one last shift, and then the multiplier is 1. I'm done, so I don't shift anymore, I don't add, and I produce a 1. Alright, so now let's assign the control. Remember, I had drawn a box that said control, and it had multiplier bits coming in, and it has pulses or shift signals and add signals coming out. We have to design it. Okay. Is that going to be a sequential system or just a bunch of gates? Sequential. Okay. Basically, it's a state machine, so let's design it. Now let's go back and continue with 4 bits, and you'll see why I'm choosing only 4 bits. Alright. I said my inputs are going to be the multiplier bit. N was my start signal. I didn't call it S because S was used for shift. My outputs are add and shift. I'm not going to take care of the done yet, for a reason I'll show you. Okay. So let's assume the inputs are just the multiplier and the start. The outputs are only whether I add or shift or neither. So before I get an N of 1, what do I do?
Nothing.
Nothing, meaning I remain in exactly the same state. Let's call that state, the rest state, as we always do, as 0. The start signal is 0. Does it matter what the multiplier bit is? No. So I'm going to call it X, or you can list 0, 0, you can list 1, 0, but that means X 0, right? So, while N is 0, I stay on the waiting state, and what are my outputs? Do I add, do I shift? No, you do nothing, as Andrew said. So the outputs are 0, 0. So then 2 things can happen. Let's say now the start signal came in. So N is 1. M can be one of 2 things, 0 or 1, right? So let's say it's 1, like in this example, the multiplier is 1. If I start it, the multiplier is 1, what is my output?
0, 1.
The multiplier is 1, what's the first thing you do after you look at that? You add. Right here, I didn't shift yet. The first thing you do is add. That's why we look at the multiplier bit, to see whether I add or I just shift. So I add, meaning the output is 1. Do I shift? No. Again, this says add 1, shift to 0. Okay? Let's call it S1. Now I said, I did start, but now my multiplier is 0. What's my output? 0, 1 indicating don't add. Why don't I add? Because the multiplier is 0. It's like this step, from here to here, I didn't add anything. Is it this same state or is it a different state? It's a different state. Actually, let me make this smaller because it's not going to fit. S2. All right. I already started. Once I start, what do I have to do?
You gotta finish.
You gotta finish. So now I don't look at the start anymore, because my multiplier and adder has to keep working until it obtains the final answer, regardless of how many times you press the button. Once it starts, it has to finish. So how do I represent that on my end? X. Doesn't matter anymore if it says start or not, because I already started. Okay? What did this signal indicate? Add. So I add. What do I do after I add? Shift. Always shift after you add. Doesn't matter what M is. No? You only look at it to see if you add or you only shift. Once you add it, you have to shift, regardless of what that was. So if I took this path, you don't even have to look at the multiplier anymore. And the output is 0, 1, indicating I have to do what? Shift. Is that a new state or is it a state I have?
S2.
That's a new state.
Why is it a new state?
Because
you
you
shift.
Okay, yeah, that's it.
Hmm?
You should be saying,
you had,
It's the state. Why would I need a different state? All right. If I have 4 bits, and we do this the slow way, I would have this same diagram replicated 4 times. You follow that? Because how many times do you have to add and shift? 4 times. So it's basically a replica of this 4 times. I'm not going to draw it. There it is. It's replicated 4 times. It's very symmetric. Right? Okay. If I have 32 bits and a 65-bit accumulator, how many of these trios am I going to have? Huh? 30. I'm going to have 32 of them. 4 bits, I have those things 4 times. Right? Why? Because I haven't used a stop signal. So the state machine itself has to know I got to go through this 4 times and then I'm done. Follow what I'm saying? Your state machine. Okay, if I come out of here, and let me go ahead and do it. Let's say coming out of here. Should I go back to a 0, should I go back to a 1, or should I go to a new state?
It depends.
Hmm?
Wouldn't it depend on the inputs that you get?
No, it doesn't depend. I just told you, there's gotta be a way to keep track of how many shifts happened, right? So, if, let's say we go back here or go back there, you lose the information of how many times you shifted, correct? That's why I have basically this diagram 4 more times. So that after the 4th, then you go back to the original state. Whenever you go back to the original state, the done signal is generated. So, yeah, don't make me draw it, just copy that 4 times. Right? Times 4 because we only had 4 bits. So we go from here to here. Let's say it's always, let's make it easy. Let's say it's a bunch of 1s. If it's a bunch of 1s, I have to say add, shift. That's my first shift. But it doesn't know it because it's a state. Then add, shift, add, shift, add, shift. Once you've done that 4 times, you're back at the, let me wait for the next start signal. So the state diagram itself is sort of counting the shifts. That's why I have 4 replicas. But having 4 replicas is really stupid, don't you think? Especially if you have 32 bits. Then I would have 32 replicas that count basically how many shifts have I done. Yes, Brian?
So I can't see that back here, but,
Okay, I'll copy it and post it. Hey,
now I have a question,
it's
so
too
you
big
you
to put in
said,
here. What?
you said, you multiply 4 times, So it'd be S0, S1, S2, and then it would be S0, S1, S2?
No,
Okay,
you gotta call them
different.
different,
Okay.
it's the replica but with new names.
Okay,
Because the state information tells you how many times have I shifted. So it's internal. Internally, I don't have an extra counter for the shift. The state itself is telling me how many times I've shifted, right? The states need to have different names, okay? So it would be another one with S3, S4, S5, S6, S7, etc.
So you're just treating S2 as S0 essentially, so you have two states coming from S2?
Yes.
And then, yeah.
So, yeah, this one would go to two new ones, the two new ones would go to two new ones, and eventually the fourth time it goes back. I'll post it, I'll make you drive, because then I have to delete everything again. Either the number of states tell you how many shifts, or what would be a better way? Again, think of 32 bits. If I had an example of 32 bits, we can do it by hand, right? It's just very long. Okay. But if I had to draw this, I would have an enormous diagram, because I have to count until I get to the 32 shifts. After the 32 shifts, I go back to 0. That's a very big diagram of basically exactly the same thing. So instead of doing that, what do we do, Eric? Build a counter separately, so it's like a control made out of two controls. This control that simply says, do you add or do you add and shift? And another one that simply counts how many of those shifts were generated. After the fourth one is generated, it says stop. Okay. And it's the fourth one because we started with the most significant 4 bits. That's really how we do it. So either this replicated 3 more times, meaning the state itself contains the shift counter. Four times. Or, much better, you just assign basically the one piece and count. So I'm going to do that one. So this is the add shift control that all it does is produces the A and the S signal. It's sort of a